This video covers Stat 454, Chapter 4, Section 6, minimization problems. Recall the previous high concept of the simplex method was one of steepest ascent by choosing the variable with the most positive coefficient in the objective function and then deciding the most that variable could attain. We could use elementary row operations to eliminate that variable's appearance in the objective and all other constraints, maximizing the objective with that variable while simultaneously eliminating its effect later on in the problem. That was a process of steepest ascent. That process worked because we were choosing maximization problems. So now we're going to try and minimize using a similar process. Let's try and use these ideas to minimize this LP. Minimize z subject to 2x1 minus 3x2, subject to all of those constraints, x1 plus x2 less than or equal to 4, x1 minus x2 less than or equal to 6, and x1 and x2 both bigger than or equal to 0. Now, similar to the last process, the main process in the simplex method, we need to ensure that all of these constraints are in standard form. So I am going to add slack variables that will force the standard form onto this LP. This is what the LP looks like when I include the slack variables associated to each of the constraints. x1 plus x2 plus s1 equal 4. x1 minus x2 plus s2 equal 6. Your textbook lays out two methods for solving LPs. And the first one is a conversion method. And it relies on the idea that maximizing the function f is logically the same thing as minimizing the function negative f, and vice versa. So we could write maximize negative f as being the same thing as minimize f. So turning minimize f into maximize its opposite, and then performing the usual steps in the simplex method should give us, or will give us, the maximum value. This is what the LP looks like when you convert z into negative z for the maximization problem. After this, everything works exactly the same. Convert the LP into its tableau form by moving all of the coefficients in the objective function to the left-hand side. Here's the simplex tableau that appears. Notice that I choose to write the basic variable for z as negative z equals 0. Z is alone in a column by itself, and I can read the right-hand side off of the column. After this, every process works exactly the same. You still choose the entering variable as the most negative coefficient in row 0. That's going to be associated to x2. And then you calculate the pivot row as usual. For row 1, you have a ratio of 4/1, which equals 4. And for row 2, you have a ratio of 6/-1, which is -6. Remember that these ratios need to be non-negative. Recall that these ratios need to be positive. That would make row 1 the pivot row, and then you'll use elementary row operations to cancel all of the appearances of x2 in rows 0 and 2. Here's the tableau that arises after performing those optimization or elementary row operations. Notice that you can read the basic variables of negative z equals 12, of x2 equals 4, and of s2 equals 10 right off the list. This is where you would check for the next iteration. Notice that the coefficients of x1, x2, s1, and s2 are all non-negative, which means that we found the optimal tableau. So the maximum value of negative z equals 12 occurs when x2 equals 4, s2 equals 10, and x1 and s1 equal 0. But of course, we were not solving a maximization problem. We were actually solving the minimization problem. So this is the same as minimize z equals negative 12 with these values, giving us the minimum value for z. The method your textbook describes as method 2 is a method that I like to call steepest descent. So in the previous sections, we were thinking of the simplex method as traveling across the edges of this constraint region in the direction where the slope of the objective function was steepest. That meant a most positive coefficient in the objective function, which meant a most negative coefficient in row 0. If we want to turn this concept into steepest descent or a minimum problem, then we want to choose the most negative coefficient in the objective function, which corresponds to the most positive coefficient in row 0. Here's the tableau that arises when you bring the constraint, the objective variables to the left-hand side of the objective function. Notice the presence of the negative sign on the 2, the positive sign on the 3, and the positive coefficient of z. Remember that we want to choose now, in this form, the most positive coefficient in row 0. That is again variable associated. That is again the coefficient 3 associated to the variable x2. Everything else follows through exactly the same as the regular simplex method. The only difference is you're choosing a different entering variable. This completes all of the discussion for minimization problems.